Brian had two assignments. This is the second part of it, which was the relationship of zeta, tau, and theta on a root loci plot. So the first part is talking about the relationship of zeta and theta. And as you can see here, here's a graph of if it was the root loci with the real axis, real values being on the x-axis, and your imaginary being the y-axis. As you can see, theta is just a measurement of cosine theta equals zeta, because if you look at the length is 1 over tau, and you also know that on the real axis that length also measures out to be zeta over tau. So when you plug that into a cosine equation, it just comes out to be zeta. So that was the first part. And so then so that's the first part. You'll see that actually put on a root loci plot. And then the second part was a decay ratio, and that's the equation that we use for decay ratio from the book. As you can see, as the zeta value is what we were varying, you can see the angle changes, and the decay ratio also changes. So depending on what your zeta value is, it's going to affect your decay ratio on the overall system. So here's a root loci plot. As you can see, there's the different degrees. Starting out with for a decay ratio, that's the 90, so that's zeta equals 0. And then as you increase your zeta, you can see it gets lower and lower, and it comes closer to a critically damped system versus where it's up at 90 degrees, you are at the ultimate. So some observations: the smaller the angle, you get a smaller decay ratio and a faster settling time out of it. So that's why it's better to have a lower angle versus a large angle where you have a large decay ratio and a slower settling time. And then again, at 90 degrees, the decay ratio is 1, and you actually don't get any settling. That's it.
Anybody else? 3, y'all are ready? Oh, we're going to go back to 3. This ought to be very good. I should have said that. Never mind. I shouldn't have. I shouldn't have biased your mind.